Okay, you can also find inverses algebraically. You don't need the graph to do that. I'll take you through the steps here. First off, we're going to use y instead of f of x. Okay, then, and this should make sense when we did this diagram earlier, where our x values are our y values of our inverse, etc., etc., etc. It should make sense that in our second step here, we need to interchange our x and y values. Then we're going to solve for y, and we're going to use the inverse. We're going to substitute that back in for y because that's what we're looking for. Okay, so let's take a look at the function that we looked at on the front page that we had the graph for. And we're going to find its inverse algebraically. So what I'm going to do is I'm going to substitute the y in for the f of x. Okay, then I'm going to switch the x and y's. Then I'm going to solve for y. So I'm going to go ahead and add 1 to both sides. I get y plus 2 cubed equals x plus 1. Then I'm going to need to take the cubed root of both sides. Okay, we get the cubed root of x plus 1 equals y plus 2. And then I'm going to subtract 2. So I get the cubed root of x plus 1 minus 2 equals y. And again, now that we've solved for y, we want to substitute it back in, substitute the inverse of f back in, because that's what we're looking for here. Properly answer the question, and that's your answer. Now that function right there is actually the graph that we have in blue on the front page, or I had in blue on the front page, that you could actually obtain just by shifting and moving things around. Okay, like we did in the last chapter with the transformations. Alright, here's a little more difficult example with a kind of tricky ending. We want to solve for its inverse. I'll just tell you right now it is 1 to 1, so it does have an inverse. You need to check that. But I'm going to substitute the y, and then I'm going to go ahead and interchange the x and y's. So I'm going to have x equals 2y plus 1 over 3y minus 2. Now remember, our objective here is to get y by itself. So like other equations that we've solved for this year, when you have a rational expression, probably the easiest thing to do is multiply both sides by the common denominator, and I'm going to distribute this x, so I get 3xy minus 2x equals 2y plus 1. Okay, because these will cancel each other out. Alright, now remember, we're trying to get y by itself. So I'm going to pull all my y's over to the same side. Okay, and anything that doesn't have a y, like this 2x here, I'm going to pull to the other side. So I'm going to add 2x to both sides. Now, this is probably the trickiest part. Notice that both of these terms have a y with them. And this is the part that students usually get hung up on. We're going to factor a y out. That's how we get the y by itself. Okay, and we get 2x plus 1. And to get y by itself, we're going to divide both sides by 3x minus 2. We end up with this. Y equals 2x plus 1 over 3x minus 2. Now, hopefully you're noticing something kind of odd here. Well, as we write our final answer, we get this. Okay, which just so happens to be also our original function. Well, that doesn't always happen. Okay, what this is telling us is our original function is already symmetrical with the line y equals x. Okay, so if we were to graph our original function, we'd see it's symmetrical with y equals x, which makes its inverse, when you reflect it over that, end up right back on itself. Again, this doesn't always happen, but in this case, it does.